Welcome, everyone, to the Tucson Amateur Astronomy Association monthly general meeting. We're here in Stewart Observatory Auditorium. We're here the first Friday of the month. And here in the room, we've got members joining us. We also have members joining us on Zoom. And we have guests that are joining us on social media. So welcome all of you. My name is Ed Foley. I'm the president of TAAA. And tonight we've got a couple of interesting things for you. David Levy, are you with us? Answer by chat if you are, and we'll make you live. Well, we don't have a good substitute. Does anybody have any poems prepared? I'm not a good poet. David has made it a habit of starting us off with a poem, so he had said he would be here, but David, okay, maybe not. No. Well, in that case, we will jump right into our main presentation, if that's okay with Sean. Okay. Tonight, we have a guest speaker that is currently a postdoc fellowship member here at the University of Arizona. But we will be losing the speaker to the Rochester Institute of Technology in the fall, but we are fortunate that he is still here. And he is, I guess, he will be giving us the big picture, I guess, if you will. His topic is the Milky Way Galaxy and the epic journey of the Milky Way. So a very big picture presentation. Dr. Sean Linden, please, Sean, give us your view of things.
Thank you so much. Well, first, I just want to thank you all for having me. Yeah, it's sort of lucky that I'm here this weekend. I'm already living up in Rochester, and I'm sort of back to escape the cold this week. So yeah, I was super lucky that I got the opportunity to talk to you today about one of my favorite topics, which is the story of our Milky Way galaxy. How we got to be where we are today, and where we're going. What's the future for the Milky Way, for our galaxy? And so here is just sort of an artist's rendition of the Milky Way galaxy, the one edge-on disk you see here, and the closest galaxy to us, which is Andromeda. And Andromeda is going to play an important part in this story. But before we get there, I want to start from the beginning and take a big picture approach. And so here is actually where the Milky Way starts. You know, the Milky Way, where we are born, is a tiny fluctuation at the beginning of the Big Bang, 1 part in 30,000 on this map, a tiny little change in the density in that part of the universe. And from that tiny, tiny overdensity, galaxies begin to grow. The first stars will form, and then the first galaxies. And slowly but surely, the universe starts to take shape. And here is where we begin that process. And over time, with observations and models, what we've come to understand is this sort of big picture of what cosmic history is. So cosmic history starts with the Big Bang, and then you get this cosmic microwave background, which is what I was just showing you, this sort of surface, this first light that comes after the Big Bang. And then from there, the first galaxies and stars begin to form, and they start to ionize all of the gas that surrounds them. And surely over the course of another few billion years, the universe takes shape and looks like galaxies that you might sort of recognize today. And so what we want to understand is how the Milky Way goes through this process and what we have in store for us. And so one of the reasons that NASA built the James Webb Space Telescope was to answer this very question. And so for comparison, here on the left-hand side is the size of the Hubble primary mirror. You see it's about slightly larger than a person. And this is a telescope that's been operating in space now for 33 years. It, by most metrics, is probably the most successful, science mission that NASA has ever done, and has produced thousands, probably hundreds of thousands of papers at this point and scientific results. And so for scale, you can see what NASA actually launched in 2021 and how it compares to what the Hubble is. You can see that JWST is enormous. It's much bigger. The primary mirror and the collecting area is significantly larger. And what really that allows us to do is to look further back in time than what we ever could do with previous telescopes. And so here is just a timeline and sort of an approximate depth back in time that different observatories were able to look. And so in the 90s, ground-based observatories were able to see as far back as about redshift of 1, which was about 6 billion years after the Big Bang. Hubble then came along in the mid-90s, and the ultra-deep fields, which was a spot in the sky that Hubble stared at for thousands of hours to look as deep as they could go. That got us all the way to about 500 million years after the Big Bang. And JWST, when it launched on Christmas morning of 2021, has now been able to find galaxies merely 100 million years after the Big Bang. The highest redshift galaxies now detected with JWST are, at approximately redshift of 10.5 or 11. And so we're really probing those earliest phases right after the Big Bang happens, those sort of early galaxies with the bubbles I was showing. That's what we're actually starting to see with JWST. And so before JWST even launched, one thing we did know was that when we look back in time, what we saw was a lot of galaxies that looked like mergers. They were in pairs. They had disturbed morphology. You see, in some cases, they had, light that connected the two galaxies together. But, one of the things that, as great as Hubble is, these are galaxies at, 7 billion years after the Big Bang. And, they look sort of fuzzy. Oh, thank you very much. Yeah, it looks a little bit clearer. Even with Hubble, which up until JWST was the highest resolution image that we could take in space, these galaxies look a little fuzzy. Now with JWST, we've been able to actually resolve all of these galaxies into their individual knots of star formation. And so now you see multiple galaxies, you see streamers of gas, you see these compact star-forming knots. And so what JWST has given us, even in the first few years, is that galaxy mergers occur at all redshifts. And they are an important part of building up galaxies, of changing galaxies, of transforming galaxies from these weird kind of little dots that you see here to these expansive and grand collisions and train wrecks that you see at redshifts today. And so one of the main processes among several processes is galaxy mergers. And so the basic idea actually that Hubble put out in the early 1900s was that elliptical galaxies actually evolved into spirals. And so his picture was that the galaxy started off as an elliptical in these tight balls of stars, and then as they aged, they would unwind themselves and become the spiral galaxies that we see. Well, it turns out that that was actually totally reverse. It turns out that elliptical galaxies are mostly made of old stars, stars that formed a very long time ago, early in the universe's history. And spiral galaxies are primarily made of young stars, stars that formed recently within the last billion years or so. And so as it turns out, the picture was reversed. And as you can take two spiral galaxies, and when you collide those two spiral galaxies together, and the combination of those two combines into one system, what ends up happening is that the resulting galaxy looks very much like an elliptical. And so what we now realize is that this is an evolutionary sequence, just not in the way Hubble thought. As it turns out, what we know is that mergers allow us to transform spiral galaxies into elliptical galaxies. And so again, we see that this is an important process in how galaxies evolve over cosmic time. And so our Milky Way, being one of the many billions of galaxies in the universe, has a very similar story. And so here is the Milky Way. Down here on the right is the Milky Way with the large and small Magellanic Clouds. If you've ever been in the southern hemisphere on a clear night, you will see the clouds. They're sort of dwarf satellite galaxies of the Milky Way that are falling into the Milky Way and are actually going to eventually sort of be eaten up by the Milky Way's gravitational potential. But right now, where they are is they're still sort of further enough outside the center that we can still see them. And as I said, our closest major galaxy to us is Andromeda. Now, Andromeda, you can see Andromeda has its own population of small satellites around it. And also, very importantly, Andromeda has its own companion with it called Triangulum. And it's not just that the Milky Way and Andromeda are going to interact. It's that the Milky Way, Andromeda, and Triangulum are going to all interact together, all merge together, and form a galaxy together. And so we know, based on how the galaxies move, we know that the gravity is too strong and that eventually this system of local group galaxies will merge together. And so, but we can't wait around for another 7 billion years for that to happen. If we want to understand what it looks like, and so here is actually what the collision scenario looks like. This sort of point where the Milky Way actually impacts Andromeda is about 4 billion years away. And you can see a Triangulum is going to come in sort of along a pendulum and interact with the two pairs. And so where are we in the Milky Way? So the sun formed about 9 billion years ago. So along this sort of timeline of the universe, we see that the sun formed right around here when the sort of after the first galaxies have been born, but sort of in the intermediate part of the universe when the galaxies were taking shape. This is when the Milky Way was sort of an adolescent galaxy, and this is when our sun actually formed back then. And you can see where we actually are in the Milky Way. And so in the right-hand side, I'm showing what is a cartoon ultimately, but is based on lots of best sort of data that we have to reconstruct what the Milky Way galaxy actually looks like. It's actually enormously difficult for us to make pictures of what the Milky Way looks like because we live within it. And sort of trying to see the forest through the trees type of a situation where it's very difficult for astronomers to make detailed maps of what the Milky Way looks like because we can't view it from this angle, right? We live within, along the line of sight. But we think this is basically what the Milky Way looks like. It has two prominent spiral arms, and we sort of live in between those two major spiral arms. The Milky Way is about 100,000 light years across and has about 200 billion stars, of which one is the sun. So, like I said, we can't wait around for another 7 billion years for the merger of the Milky Way, Triangulum, and Andromeda to take place. But we want to understand this process. And so what we developed in the early 2000s was a survey called the Great Observatories All-Sky LIRG Survey. So it's an acronym within an acronym, but LIRG stands for Luminous Infrared Galaxy. And so really what is important about luminous infrared galaxies is that they're really, really bright and they're really, really dusty. And as it turns out, if you ask yourself, what are the brightest and dustiest galaxies in the nearby universe? Give me all of them. And that's what we asked Hubble and NASA to do, is give us time to look at all of these galaxies. And in the early 2000s, we started this survey. And you can see for yourselves what most of these galaxies are. In fact, nearly all of them are major mergers between two spirals that are coming together and merging, very much like what the Milky Way and Andromeda eventually is going to be. And so what we have here is a sample of 200 future Milky Ways, 200 possibilities for what the Milky Way could be and what the fate of the Milky Way could look like. And so this is a representative sample that allows us to chart the progression of the Milky Way's merger in sort of representative galaxies. And so what this looks like in practice, and so the GOLS survey is the 200 brightest galaxies, like I said, and we've observed them with essentially every ground-based and space-based telescope that you would ever want to use. And so what you can do when you have 200 galaxies is you can construct what we call the merger sequence. And so, on the top left, the two galaxies start off as sort of a widely separated pair, much like you would see the Milky Way and Andromeda today. And then as we go, we find examples within the survey at each progressively more advanced interaction stage. And so as you go from the top left over to the top right, and down to the bottom left and over to the bottom right, you see the progression of the merger, and you can see what happens as two galaxies merge. And what happens is you see in the middle panels, you see all of these blue stars. Those are all the stars that get formed as the collision takes place. And then you can see that after the collision in panels 5 and 6, the young stars are sort of going away, and you're left basically with these smooth, featureless, sort of redder galaxies that eventually evolve and become ellipticals. So we can use this survey to understand what is going to happen to the Milky Way and understand more in general how mergers shape galaxies across the history of the universe. And so that is what our mission is with the GOLS survey. And one of the things that makes GOLS so fun and so unique is you really need to collect multi-wavelength observations in order to understand these systems. So on the left-hand side, I'm showing an HST image of one of our mergers, or basically what you see there is one galaxy on the right and sort of nothing there on the left. And as you go to longer and longer wavelengths, so redder and redder wavelengths, what you see is that actually the galaxy on the eastern side, the one that you cannot even see with HST, that's the one where all of the light is coming from. If you were to take a total amount of light, most of the light is coming from this galaxy, the galaxy on the left-hand side. Not the one that you can see with your eyes, not the one that Hubble can see, but the one that the longer wavelength telescopes can see. And so you really need the combination of all this data together. And you'll see what I'm talking about more in a few slides. So when JWST launched in 2021, the Great Observatories All-Sky LIRG survey was fortunate to be one of what they were calling the early release science program. So our group was one of the first small handful of teams that got to take data with the telescope when it first launched and be some of the first people that got to actually use data from the telescope. And so what we did is we chose these 4 galaxies as the galaxies we were going to study in our early release program. And part of that program meant that we observed all of these galaxies with every instrument that JWST had as part of the way to test the early capabilities of the instrument. And so what I'm showing here is actually the images that we have gotten from JWST of these galaxies. And you can see that sort of hexagon pattern of light. That is due to the actual telescope itself, because the pixels in that region are so bright that they actually saturate the telescope. And in both of these two galaxies where you see that pattern, both of those have very strong black holes. And I'm going to talk a little bit about black holes in a second here. But black holes are actually a very important part of the merging process. And so one of the other things that we've learned when galaxies merge, it's not just that new stars form and that they collide and gas gets flown everywhere. It's that also the black holes at the centers of the two galaxies combine to form one supermassive black hole. And that black hole often goes through a phase which we call active galactic nuclei. And this is a phase where gas will be blown out of the galaxy violently by the black hole. And so the black hole, we also have to worry about the black hole when these mergers happen and what's happening at the very centers. And you can see in two of these galaxies, we have very, very strong black holes. And in two of them, we have mostly just really strong bursts of star formation. So I'm going to go quickly through some of what we found with these four galaxies in the first few years with JWST. And I just want to point out that when we talk about spectroscopy, the best way to think about spectroscopy is you think about the light that you get from a galaxy being a combination of all of these different wavelengths. And so these pretty images are combinations of light from different wavelengths all stacked together. And so that's what a spectrum is. It's just one long continuous sequence of light stacked at discrete spots along a spectrum. And so what JWST allows you to do is not just to make images at one fixed wavelength, but to make images at any wavelength that you want along the wavelength coverage of the instrument. And so this is an example here of what this looks like. You can see on the left, we have our pretty galaxy, our merger there, NGC 6240. And with JWST, you can actually break down what the central region of that galaxy looks like in different slices along the spectrum. And so the spectrum essentially allows us to make these multi-wavelength images and study things as you change in wavelength. And so I just wanted to sort of show that before we sort of get to some of these results. So here is TAAA 96. TAAA 96 has this region that you see highlighted in the box, which is D1. D1 is essentially the brightest, most massive star-forming region that we have ever really observed outside of like around the Milky Way. And I'll show you an example of essentially what this region we think looks like. D1 for a long, long time has been thought to be a hidden black hole in the middle of this merger. But as JWST has shown, it actually seems that in many cases, this thing is so extreme, it's actually not not a black hole, that we think that this thing is actually just this incredibly intense star-forming region that we discovered with JWST in the center of this galaxy. And it would basically look like this. So here's an example of a massive star-forming region in one of the Magellanic Clouds that I was mentioning before. It's 30 Doradus. It's the most massive star cluster near us in the Large Magellanic Cloud. It has about 500,000 suns contained within this individual cluster of stars. What we have found here in D1 in TAAA 96 is something like 100 million stars collected into one small region. So it's incredibly extreme, and we think it is basically due to this violent merger that moves gas around and compresses gas and forms these incredible sort of regions. Another galaxy, one that I actually already showed when we were talking about the multi-wavelength nature of the survey, is VV114. And so I want to just play this movie here, which flips back and forth between HST and JWST. And what you see, again, with HST, the left-hand side, we totally didn't see anything there. It's all red, totally dust obscured. HST is not able to study that region. And with JWST, all of a sudden, boom, that galaxy that's hidden behind all of that dust, it pops right out. And it allows us to actually study the details of that galaxy in ways that we were never able to do just with Hubble. And that's really the revolution that JWST has brought us, is allowed us to study these violent mergers in incredible detail, because we can now look through all of this gas and this dust. And so we discovered another 20 of these very, very massive star clusters in this galaxy. And NGC 3256, again, a galaxy where we have a ton of star clusters. And again, I want to just highlight on the left-hand side with HST, the southern nucleus of this galaxy. You can see here at the top is the full system. There's actually two galaxies hidden in here. The southern galaxy, again, is completely hidden behind dust in Hubble. We cannot see it. Now with JWST, we can see right through all of that dust. It's completely gone. And you can reveal that there's this massive amount of star formation going on behind this sheath of dust. And so we're actually able to take spectra of these individual compact knots. And what we were able to learn from that is we're able to actually build up a picture of how we think stars are forming in the very central dusty regions within these galaxies. And so this is our sort of best picture that we have for how star formation takes place in the sort of hearts of these dusty luminous infrared galaxies. Is that, massive stars begin to form. They're very, very bright in the infrared. After about 4 million years, the energy that the stars produce is enough to blow away all of the surrounding gas and dust around it. And that by about 8 million years, the star cluster has removed all of the gas and the dust around it. And this helps us better understand how the energy from stars propagates out into the interstellar medium of the galaxies themselves. And so this is sort of the research that we've been able to do with the JWST observations that we've collected over the last few years. And the last one I want to talk about is one of these very exciting black holes, NGC 7469. On the left-hand side is the JWST observations. You can see it's got this very strong point source in the center, and then there's this sort of ring or spiral around the galaxy. And if you actually zoom in, what you see in that top little cutout right there is that there's a ring of star formation surrounding the black hole. And so in this case, not only do we have intense pockets of star formation, but we also have an intense black hole. And so this is an example of where the black hole and the stars are forming together. And you can see here we're able to actually map this ring. So you see these sort of black contours sort of form the shape of a ring around the central source. And that allows us, for the first time ever, to map the amount of gas and dust that is in this ring. And so we were able to now sort of produce this kind of cartoon view of what we actually think is happening at the center of this galaxy. We have this active galactic nucleus, which is launching this intense outflow. And that's why the galaxy is so bright. But then you also have energy, which is being deposited into the surrounding ring. And so the properties of the clumps that form in the ring are very distinct and unique relative to sort of how we think stars form in sort of more quiescent or sort of normal galaxies. And so we think that the Milky Way will go through a phase very much like this, with its neighbor. We know that Andromeda and the Milky Way both have very supermassive black holes. And we know that both of them will eventually merge and produce active galactic nuclei activity that could look very similar to this. So, revisiting the galaxy merger sequence, we start with the initial encounter. As the galaxies interact, we get tidal streams where gas and dust gets flown around. As the two nuclei then come together, you start to get black hole activity, and you get even more gas and dust that gets pushed out and flung around. And then eventually, when all of the gas has been used up or ejected from the two galaxy merger, eventually what it will look like is something that sort of resembles an elliptical galaxy. And so that brings me, with all of this information in hand, with all of the observations that we have, here is our best guess, our best simulation for what we actually think the Milky Way and Andromeda is going to look like. So a billion years, the clock starts today. So this is at time 0 right now. And this will be now into the future. Here's the Milky Way. 500 million years. I remember I said it takes about 4 billion years for the galaxies to collide. We're 1 billion years in. Andromeda is getting closer. As the two galaxies get closer and closer, Triangulum now starts to come in. At 4 billion years, now Andromeda is really right in our backyard. And you can see that we're approaching the merger, and there, and material will get flung out. And eventually, we think that the gravitational pull will still be strong enough, it'll come back in, more material will get flung out, the black hole will activate, and all of a sudden, you'll be left with an elliptical galaxy. Milkomeda will be sort of a round ball of old stars with Triangulum, maybe lives, maybe not. Actually, it's pretty unclear. The models are sort of unclear about Triangulum. In some models, Triangulum comes in. In some models, Triangulum gets flown away. In some models, Triangulum hangs around for a little while. So I don't know if we'll be around long enough to know the answer to that, but so at the very, very end, I just want to show some quick images that I really like to show that NASA produced, which is sort of taking snapshots from that simulation and projecting what the night sky would look like if you, let's say, went out into one of these, crystal clear Tucson nights and, you took some deep exposures. You might see something like this today or tonight. In 1 billion years, the night sky might look like this. Another 1 billion years, humans were still around, the night sky would look like this. If humans still are around 4 billion years from now, the night sky might look like this, which now you can see all the mess and the chaos, and you're getting gas and dust is getting whipped around. Another 1 billion years, or maybe even less. There's maybe only a couple 100 million. The galaxies are still very chaotic. Another couple 100 million. The two galaxies have separated themselves again, like we saw. Another couple 100 million. And now you're starting to see the impact of the black hole. All of the gas has been removed. And this is what the night sky is going to look like. You won't be able to do your dark sky astronomy anymore. This is what the background of the sky will look like. We will live within this sort of weird elliptical. And then eventually, this is what the night sky is going to look like in 7 billion years, if Earth is, around long enough to see that. And so I just want to, another thing that I think is interesting is you can make an image of what Andromeda looks like. This is just sort of an amateur image of Andromeda. It looks relatively huge on the sky, but one of the things that we don't realize is that the halos that surround these galaxies are incredibly massive. And so even though Andromeda is still only 4 billion years away, the halo between the Milky Way and Andromeda, the two halos, are actually very close already. And what that actually looks like is here. And so here is now actually what the halo of Andromeda looks like with X-rays. You can see that the halo is so much bigger than that Andromeda, which is that small little nub at the center there. So the actual amount of gas around Andromeda that's right in our backyard already is huge, right? These things are very much already mixing together. We see evidence of that already. And my last thing, if you're interested in all of this, two of the heads of our collaboration wrote a Scientific American article about the fate of the Milky Way and highlighted many of the things I talked about today. So we're very grateful to Scientific American. We were the actual cover article for this issue. And so, yeah, you can read more about my talk today there if you're curious, or of course you can contact me. Yeah, so thank you very much for your time. I really, really enjoyed it, and I'll take any questions that you had.
We usually start with questions in the room. If you have a question, raise your hand. We will get a microphone to you so that you can ask your question, and everyone in the room and online can hear your question. Oh, here's one.
Thank you. Periodically, I seem to read recalculations of the sizes of Andromeda and the Milky Way and their respective magnitude. How sensitive are these models to those assumptions?
So problem is getting the distance to Andromeda very accurately, which is difficult to do. You know, because we're merging with it, our dynamics are coupled to its dynamics, and so getting very, very, very accurate distances is more challenging than it may be seen. So there is some uncertainty there. I mean, there's been tons of work with Hubble mostly, but now even maybe some with JWST to accurately measure the distance. But that is really where most of the uncertainty lies, not as much in the models, because the mass, we think we know the masses of these galaxies relatively well within, 10%, 20%.
Testing. Okay. My question is, so towards the beginning of your talk, I realized this might not work out too good for us humans on Earth. And so I'm wondering what type of studies, if any, are going to happen as it relates to the gases from Andromeda as we get closer and closer. How are those gases going to affect us humans? Will that be safe for us? And at what point do we think we might be in danger, right? So you said it's violently explosive and all of this stuff. Will there be like reverberations? Like, what do we think the actual experience might be like?
Yeah, very, very great question. Thank you. It's not entirely clear. So like 4 billion years is how long we have approximately until the Milky Way and Andromeda get close, really close. And I will say that one of my favorite little facts about how big galaxies really are is like, let's say you and I were to each have like 1 grain of sand, like 1 grain. And I asked you, okay, we're going to throw our grains of sand. And the chances that our grains of sand hit each other in midair, that's actually the chance that the sun or the earth would collide with something in Andromeda, right? It's mostly empty space moving through each other. The reason that it looks so violent is because the gas doesn't act like that. The gas is kind of like molasses. So as the gas moves through, it gets stuck together, it sort of sticks, right? But the stars are just gravity. And so, you know, what we might experience on Earth is probably not much. Now, it also depends on how much longer we think the sun is going to live. So if the sun has another 4 billion years, maybe we make it to this point. You know, does human society live that long? Okay, we put that question aside, but let's say it does. There could be a chance that we could get to that night sky I showed you with Andromeda. And, you know, I don't know if like it would be hotter on Earth. I think the night sky would be brighter. I think, you know, it's a very interesting question to ask, like what would society look like if we were born in an elliptical galaxy, if our night sky always looked like that, like it does at the ends. You know, some civilizations might be like that. But, you know, I think actually in the day-to-day life on Earth, it'll be much more heavily dictated by what's going on with the sun than anything going on with the merger. Although you might see it, it won't affect like the temperature, the tides on the Earth or anything. Like it's just we're too removed from that actually, which is crazy to think because, you know, it looks like it's coming right for us. And in the end, it sort of is kind of not as violent for us as it is for the whole Milky Way itself. Yeah.
We talk about the black hole in the center of a Milky Way galaxy. I read somewhere a couple months ago, and I can't remember where I read it. Astronomers think it's something else. Can you elaborate on that?
Well, I can say that we think that most galaxies, at least galaxies of this size, have supermassive black holes. Now, there's been a long-running debate. How early do black holes form in the universe? Do galaxies at the very earliest times in the universe have black holes? When do black holes first form? How many galaxies in the early universe have them? So I think those are questions we still are looking for the answers to. I think when you get to the very nearby universe, what we have found is that if you get to the point of being a Milky Way, you will have a black hole. It's basically, we haven't seen anything yet. And you know, it could be that a galaxy could grow to be the size of the Milky Way without a supermassive black hole at the center. But we haven't found it. I mean, it'd be cool if we did. But yeah, I mean, as far as I know, we haven't.
Okay, years ago, I heard that, or I read somewhere that if the Milky Way had been stripped of all its dust that we see, and all the dust lanes and everything, all that were removed, it would be bright enough to read a newspaper by. I'm wondering, I'm wondering how true that is, and in fact, when you mentioned at the end, you wouldn't have a dark sky, and that's, yeah, that would kind of relate to that a little bit.
It's a very fun thought experiment. I don't know. I guess it's possible. I mean, yeah. So like what this is, right, is a galaxy, or more or less 2 galaxies worth of stars without any dust. So, you know, in the situation like the Milky Way, right? Like when we look at the Milky Way now, right? Here, all of this, you know, all of the dust, right, goes away, right? Essentially in that scenario. I don't know if it would be quite as bright as the elliptical case. So maybe that might be slightly hyperbolic. I'm not 100% sure. I would love to do the math or something to find out. But it is certainly true that if you remove the dust and you just have the stars, even if they're old stars, because here we're seeing mostly young stars, and young stars are brighter actually than older stars. Here we're actually looking at all old stars, but this, you know, with this many stars and no dust, the sky would be incredibly bright. So it could be that if you just took away the Milky Way's dust, it would look very, very bright like this. Yeah.
Theoretically, if like, would gravity affect Earth differently when the two galaxies like merge? Would like gravity affect Earth
Yeah.
differently?
Yeah, as far as we can tell, we don't think so. And so this is like partly because, you know, the solar system is, you know, so tiny compared to the actual size of the galaxy, right? You know, let's say it takes light from the sun to us. It takes light about, you know, a few minutes to get to us, right? So it takes a couple of minutes for light to go from the sun to Earth. For light to go from one side of the galaxy to the other side of the galaxy would take 100,000 years. So you go from a few minutes to 100,000 years. The difference is so big, right? That as it turns out that, yeah, our gravity that we would experience won't really change. It's just dominated by the fact that we're really close to the sun. And even if the galaxy around the sun is moving around and, you know, we're still locked in kind of right next to the sun. So I think mostly gravity wouldn't change that much. I mean, I think it, you know, I'm not sure how well the models actually handle all of the details. So it's possible, but yeah, I think by and large, it doesn't affect us that much.
A couple of quick comments, if I could. I very much enjoyed your slide presentation. Your visual representation of what you were talking about, I thought was outstanding.
Thank you.
I'm math deficient, so
Me too.
visuality is helpful. Secondly, the article you referred to in your last slide, you said was published where?
Scientific American.
Scientific American.
Yep. And the QR code, I think, should bring you to the online link. Good. And I believe you can order back copies in print if it's, you know, if you're,
I'm
if
sure.
you want a tactical.
Yeah. And I know your slides are your personal property. Is there any chance of getting copies of them?
For
or
me
not?
personally, you know, astronomy is, you know, the job for me is sharing. So I'm happy to share slides. I mean, none of this is.
So if I send you,
If you wanted slides, I'm happy to share. None of it is proprietary for me. You know, it's all open.
okay, I will send you an email and we'll see what we can work out.
Perfect.
Thank you.
Dr. Linden's presentation will be on the website in the next couple of weeks. So if you
Also,
want,
you could find it there.
you can see the material again as many times as you want.
Do we have time for one more question?
Yes.
Is it true that every galaxy has a black hole?
Yeah, I mean, this is a very fundamental question. It's a simple one, but it's a very important one. And it's not clear. I think what I'm comfortable saying is that galaxies that are very massive have black holes. Like I could guarantee that. So like galaxies that have 10 billion suns, you know, we said the Milky Way has like 200 billion stars. If you have that many stars, you have a black hole. I will say that. If you have a billion stars, it actually turns out that a lot of galaxies with only 1 billion stars, a lot of them do not have black holes. Now, so we go from 200 billion, where most of them have black holes, all of them maybe, down to 1 billion, maybe none of them. And so there is a transition point as galaxies grow, as they get more massive, as they collect more stars, as more stars form in them. And I think where that transition point happens is a very much open area of research. So it's not a perfect answer, but I would say, yeah, there becomes a point where it looks like every galaxy has a black hole, but if you go to low enough mass, it looks like very few do. Yeah. Like the Magellanic Clouds. The Magellanic Clouds do not look like they have like massive black holes in them. So those are, you know, examples right there in our backyard. Yeah.
Are you continuing this work up here?
Oh,
Are you going to continue this with your new position?
yeah, I mean, so my position here was I was an independent fellow. So I've been working in the goals collaboration since I started in grad school back in 2014 to now. So this has been sort of my primary research for a very long time. Yeah, my faculty position at RIT is going to be recruiting grad students to help me with lots of new data that we have. So I was only able to show a tiny, tiny fraction of the work that we're doing. And really the hard thing is to do all of this work, we need people. And so more than anything, I'm excited to go to RIT to get students and to sort of train the next generation.
Do we have anything on
Pete?
social media? Okay. Well, you're going to need a microphone, I'll bet. Here you go.
Okay, just this is off chat, so members on Zoom. A couple of comments from Gary C. in Chile. I thought the Magellanic was a cloud.
Yep.
I'm going to assume a weather cloud, probably. And then from Laura Dunlap, great presentation. Thank you. And now for a few questions from Richard Spitzer. Did the sun or Milky Way form 9 billion years ago?
The Milky Way began its journey as far back as basically the beginning of the universe. You know, the very first stars that formed within the Milky Way that would become what we know it is today. Like the oldest stars that we see in the Milky Way are like 12 billion years old. So the first stars that formed in the Milky Way formed right away, right in the beginning. That's why, you know, the history of the Milky Way is this piece by piece. The sun, specifically the sun, formed about 8 billion years ago. But the very first stars that we find in the Milky Way are 12, 13 billion years old. So we know that some stars formed in the Milky Way from the very beginning.
And from an unidentified Zoom user, what future space telescopes are being developed and what would such telescopes allow us to do?
Great question. Yeah, there are two main things I could say. So what NASA does, what actually the US government does, is what they do is they solicit the astronomical community to create what they call decadal surveys. And so every 10 years, astronomers get together, and as a community, we decide collectively what we think the next 10 years of astronomy should look like. And we give those recommendations to the powers that be at the NSF and at NASA for them to make decisions about what they want to fund these next grand projects, right? And so that process yielded the Hubble Space Telescope. It yielded the James Webb Space Telescope. These things were born out of this process. So the last time that astronomers got together to do this was 2020. And the mission that they put forward was a success, would be basically the successor to Hubble. It's called the Habitable Worlds Observatory. And I don't have any fun backup slides to talk about habitable worlds, but actually there's a lot of people at University of Arizona doing doing the work to get ready for habitable worlds. So, you know, there's plenty of people here to talk to about it. But Habitable Worlds Observatory would essentially be at the size of JWST, if not bigger, but operating at the same wavelength as Hubble. So JWST operates in the infrared. Hubble operates in the visual, like where our eyes see. And habitable worlds will be basically Hubble 2.0. That is really not something until 2040, long term. In the next decade, NASA is doing a probe. They want to launch like a sort of $100 million scale probe, which seems, like a lot, but when you're talking about what JWST ended up costing was something like 20 billion. And Habitable Worlds Observatory would cost probably 100 billion. And so instead of spending 100 billion, what NASA wants to do in the next 5 or 6 years is spend about 100 million and launch a probe. And right now, they're going through what they're calling an institutional review, where they're going to decide if the probe is going to be an X-ray mission or a far infrared mission, so even more red than JWST. And so we will know sometime in the fall what direction NASA wants to go for this sort of late 2020s, early 2030s. But the long-term plan is to launch something like Habitable Worlds Observatory, if we can, get there. But it's one step at a time. There's a lot of technology development that would have to happen between now and then for it to even be possible. So, but like with JWST, the situation was the same. Coming into the early 2000s, they knew that they needed to build JWST, and it took 20 years of technology development to make that happen. So it would take another 20 years of technology development to make HWO happen. We'll see.
And from Richard Spitzer again, I've read recently that Andromeda and the Milky Way will miss on the first pass. Is that what your simulation shows, is the Milky Way and Andromeda seem to pass through each other, then come back to merge?
Yeah, that's right. So yeah, there has been, and this is, the simulations, are our best guess. This is active research. It is probably likely that the first pass of the Milky Way and Andromeda is actually going to be less of a direct collision and more of a graze, and that eventually they'll come back and eventually more directly impact each other. And so there probably is some work to be done. I think what the person on Zoom is referring to is actually relatively recent work in the last year or two. And the simulations I'm showing are probably 5-ish years old. So there's possibility that we could, even improve the models. Yeah.
And then a final question from Mike Tozer. When the Milky Way and Andromeda merge, will the black holes at the center of the galaxy create, for lack of a better term, two paths of destruction as the galaxies come together?
Yeah, so as the galaxies come together, the black holes will merge. And this merging process creates what they call like sort of blowout. And so if enough material gets slammed together into these black holes, the black holes will shoot material away from them in these jets, these sort of explosive jets of material. And I don't have a good, there are many examples of this. I wish I had a good one in the talk. But that sort of cone that you see coming off of that central thing, the AGN, that is what this is. So the black holes will merge, and then eventually they'll unleash energy out away from them. And that is something that will happen with Milky Way and Andromeda, yes, eventually.
That's it from Zoom.
Okay, we got 2 questions from social media. The first one, is there any risk of a rogue planet entering our solar system?
The risk would be incredibly low. But yeah, there's always a chance, never say never, but I would say I wouldn't put any money on it.
Okay, and then the last question is a little bit more general. If the universe is the fabric and it's expanding, what is it exactly expanding into? Good
question. Yeah, it's not a very satisfying. I'm not going to give you a very, well, maybe, yeah. I tend to think that the universe is everything. And that, the idea that the universe is, what is it expanding into, isn't really the right question. It's, because the universe is everything. So it just expands. It's just, the universe encompasses everything. There's no like outer bound of the universe. It is everything that exists. It's, there's no like, yeah, it sort of gets at how you conceptualize infinity. And, it's sort of, I get, I understand the thought of what is the universe expanding into. And it's something people ask all the time. And I think it's just the wrong sort of way to think about it. I think it's just, yeah, it is the universe. There's no, it doesn't create more universe. Yeah.
That's it from social media.
Okay, thank you for those questions. And Dr. Linden, thank you for coming.
Thank you.